extend to 2D system. Okay, so what does a 2D system look like? So 1D system was okay. A 2D system would look something like this. I'm just going to write it as a matrix equation. Yeah, I'll need room for this one. Okay, this is in fact equation of a coupled spring mass system. If you have two springs, I mean, you have coupling between two masses through springs and damper, then you'll have something like this. Of course, it will not have all this. There'll be zeros in there, but it will be of the order of something like this. So what we want to do here is we want to create a controller F equals minus KPQ minus KDQ dot. What would that look like? Well, it'll look like this. I'm just expanding this F equals minus KP KD. F equals minus KP11, KP12, KP21, KP22, Q1, Q2 minus, let me put it plus. Well, let me just do it this way. It might be easier. The minus out there. And then KD11, KD12, KD21, KD22, Q1 dot, Q2 dot. Okay, so these are four numbers, four parameters which you can tune. Here we have another four parameters. Okay, this gives us 8 parameters. Okay, since the system is has 2 degrees of freedom, we would have 2 conditions. So 2 critically damped conditions. Right, that is the first equation should be critically damped. That's Q1. The second system should be critically damped. So we have to make choice of 8 parameters, but there are just 2 conditions. In other words, there are 2 equations, but there are 8 free parameters. So this is what is going to be a tuning nightmare, because how do you choose? Well, there's a lot of choices you have. How can you choose 8 numbers so that they satisfy 2 conditions? Imagine 2 equations and there are 8 variables in there. So it's basically a tuning nightmare, and so you really don't want to be in the situation where you are doing this. For a 1D system, it was nice because you only had 1 condition and 2 parameters. So it was you could fix one of them and choose the other one based on the condition. But this is not going to scale. So what we do is there's a different trick which is used to do the critically damping of a system which is more than 1 dimension, and that's what we'll do next. This method is called feedback linearization, or sometimes it's also called control partitioning. So I'll write a note. So this is, okay, it is difficult to tune 8 parameters with only two conditions. So hence we use what is, I'll show in the next page, feedback linearization. It's a method of control which basically avoids this complexity of the equations. So this is feedback linearization. Sometimes it also goes by the name control partitioning. Okay, so let's look at the equation of a manipulator. And I'm not going to assume it could be 1 or 2 dimensions or 3 dimensions, just going to make it an n-dimensional equation. So let's take m q double dot plus pq q dot times q dot plus g times q equals tau. This is my equation of a manipulator, which I wrote down earlier. Now what we do is we choose, so this is the feedback linearization part, we choose tau to be in this form. M hat minus kpq minus kdq dot plus c hat qq dot times q dot plus g hat q. Okay, what are m hat, c hat, g hat? They are estimates of m, c, and g. Okay, what's m, c, and g? They're basically related to the mass of the robot. Sometimes also the accelerations has to be, or the velocity has to be taken into account for Coriolis term, and g depends on the mass, inertia, and link lengths. When a manipulator is available to you, let's say you buy it, you're not sure of these parameters. It's basically in the spec sheet, but the actual values of the parameters may be different from the physical values. So you need to estimate the values. So those are the estimates. Okay, you will probably not be fully right, but you can be close to them. So what we'll do is, to show you that this works, we're going to just assume that we have access to the perfect values for the parameters. So let's assume that we know the parameters of the robot perfectly. So c equals c hat, g equals g hat, and m equals m hat. Okay, if that's the case, then what we can do is we can substitute. Let's call this 2. So let's substitute 2 in 1. And we also know that they are perfect. So what we'll do is we'll just take the perfectly estimated value, q dot plus gq. I wrote the left-hand side of 1 equals, I'm going to put tau is this on the right-hand side of equation 1. So I have m minus kpq minus kdq dot plus cq q dot q plus gq. Okay, so the way it's set it up is this thing will cancel with thing over here. This g will cancel with this g, and you'll be left with a single equation which looks like this: q double dot plus kdq dot plus kpq equals 0. Okay, now when you have an equation like m times something else equals 0, either m is 0 or the second part is 0. But since m is not 0, the mass is not 0, the second part in the bracket should be 0. So q double dot plus kdq dot plus kpq equals 0. Okay, so this equation actually is nice, because if you expand this out, you get q1 double dot, q2 double dot, so on till qn double dot plus, okay, kd and kp are parameters you choose. Almost out of, I'll write this down, I'll stop. So these parameters are user chosen, so I'll just choose it to be kd1, 0, 0, so on, 0, kd2. In other words, I'm just choosing a diagonal form for kd because that's something I can choose. kdn q1 dot q2 dot so on till qn dot plus kp1 0 so on 0 kp2 0 kpn q1 q2 so on till qn them to be critically damped. So what feedback linearization does is there's a special way of assuming a form for the controller. This is the control equation. That is, if you apply this torque, okay, it is chosen based on looking at the equations for the manipulator, which is this. It can be shown that the equation reduces to this equation. And now when you expand this equation out, you get something like this. Q double dot KD is a constant you choose. In this case, I'm going to choose a diagonal KD and a diagonal KP. And what you notice is that these equations are essentially decoupled. So this is where I stopped. So let's go from there. So these equations are decoupled. That is, you can write them independently. So first equation is something like this: kd1 q1 dot plus kp1 q1 equals 0, q2 double dot plus kd2 q2 dot plus kp2 q2 equals 0, and you can keep doing that till you end up with qn double dot plus kdn qn dot plus kpn qn equals 0. So these are n decoupled equations. Okay, what do we do with these decoupled equations? Well, we try to ensure that each of them is critically damped. How do we do that? Well, you can control kp1, kd1, kp2, or kd2 the way you want to control them, because those are parameters which you choose. So what we'll do is we'll use those equations we got earlier. So you see this for a system. So I'll just take this equation, rewrite it as a reference. So this was the equation we got for so what we observed is if you have mq double dot plus cq dot plus kq equals 0, sorry, equals no, let me rewrite it slightly differently. Hold on. I don't need this one. Yeah, I need this one. So this is the equation after putting in the torque value. So I'll rewrite that one. Mq double dot plus kd plus c q dot plus kp plus k q equals 0. For this to be critically damped, the condition is kd equals minus c plus 2 square root of k plus kp times m. This was derived earlier. Okay, now we come to use this. So how will we use this? We'll use this for the first equation. So the first equation is this. So let's choose kd1 now using this equation here. So kd1 equals minus c. So c is something which appears as kd plus c. But if you see here, it's kd plus 0, right? So c is 0 plus 2 square root of k plus kp. k appears here as kp plus k. Here we have kp1 and there's nothing there. So it's kp1 plus 0. So 0 plus kp1. M is what appears in front of q double dot, but m is 1. So this condition is simply kd1 is 2 square root kp1. As simple as that. It's not, it comes out to be very simple. Right? In general, so we can do this for each one, right? kdn equals 2 square root kpn, or in general, we can write k di is 2 square root kpi. As long as you choose kdi to be this 2 square root kpi, you will ensure that all the degrees of freedom, 1 all the way to n, are all critically damped. Okay, so this is the thing which will drive the control. Now we will choose that critical kd and then do some simulations. Before that, I would like to show you what is known as a block diagram. A block diagram is the language with which a control theorist will communicate with another one. You might have seen them in dynamic systems and controls, but it's also been used for robotics. So what we derive there, those equations can be represented with a block diagram, which I'm going to show next. So what I'd shown here was, so let's go to block diagram. So we have equations. This is not new. This is the same equation I wrote earlier. And then this is our controller. Tau equals m hat minus kp q minus kd q dot plus c hat q dot q dot plus g hat q, where the hats in means that we are estimating the value of those m, c, and g. So the block diagram is basically something which shows how these two equations are related using a block diagram. Okay, so what we'll do is first show the system mq double dot plus c. I'm going to skip the, well, I should have put here mq q double. I'm just going to skip the arguments inside m, because then it's too many things to write here. So I'm just going to write it like this. Okay, so this is the system shown as a block, and now I need to show all the inputs and outputs to this. So what's the output from this? Well, let's put the inputs. That's easier. The torque is the input. The torque drives the system. What comes out is sensor data, which can be used towards control. So two things which will come out from this is q and q dot. Okay. Okay, now once we have, so this basically takes care of the equation 1. That's everything which is in equation 1. Now we need to show, this part is 1. Now we need to show the second equation. So that will be shown, that will basically tell you how q dot and tau, sorry, q dot feedbacks to tau. Okay, so let's see what's happening here. So we have q and q dot, which comes from the system getting multiplied with kp and kd. So let's do that first. This is the block which multiplies with kd. And let's take this. This multiplies with kp. So q dot comes here, q comes here. And so we've taken care of this part and this part in some senses. We still need to multiply. Well, we need to take this, and then remember we need to sum them up somehow with the negative sign. So I'll get it to a block which sums. Okay. Okay, so this block, I'm free to choose what I want to do, summation or negation. So here I sum it up. I put a negative here, and what comes out here is minus kpq minus kdq dot. Okay, so I've taken care of this whole block. Now this gets multiplied with m. So I need to show the m. So all the constants are the parameters such as kp, kd will show up in a square box. So similarly, I have m hat. So this takes care of this. So what comes out of this block is going to be this entire sum, this entire thing, the first term. Now I also need to multiply this with c hat. So this is multiplying with q dot. So I take q dot from here. Take c hat, q dot if you want. C q dot q dot. Now this also requires q, which means I need to supply it with q2. Let me use a different color. That way it's easier to see this. So you just do it with one color, but I'm just putting two colors, so it's easier to see. So q goes there, but q also goes into this block because it depends on q also. So q dot and q. But we're not done. We are done with this, but we're not done with G. So let's do that one. Now, the input for G is going to be Q. So draw another block for Q, G hat Q. This will only use Q. So let's put that in. Okay, so we have this. We have this. Let's call this 1. That is the 1. I should use a different symbol because the 1 is taken. Let me use A, B, and C. So let's call this A. So A is coming out here. Then let's call this part as B. So B is coming out here. And then let's call this part as C. And the C is coming out here. Okay, all of these things have to be summed. So I need a summing block. And all the sum basically gives me tau. So what I can do is draw a summing block, which would be the circle, and to it feed all these things. So let's start with the lowest one. Then let's get B. And then let's get M. So it's A. And then I just need to sum. So this tau now is showing me how the system closes back the loop. Let me move this a little bit around. There's no clutter. What comes out here is C times Q dot. What comes out here is G times Q. What comes here is M hat minus KP q minus kd q dot. Okay, so this is a block diagram. I don't know if you've seen this in before, but that's typically used to communicate an idea on how a controller is mapped to the system dynamics. So this is the system dynamics one, and then the controller basically closes the loop. So q dot are outputs. The torque is the input. So you typically need a sensor to measure the outputs, right? The position is measured by maybe an encoder. The velocity is measured by the sensor, which measures the position, but then by doing some clever differentiation, you can get that. The inputs is basically the actuator, a motor, or a pneumatic system, a cylinder, piston cylinder, whatever you want will be the actuator. So a system will always have an input and output. Output means sensors, input means an actuator. Okay, so what we'll do next is we'll see how to apply what we did on various problems. So this was a spring mass damper. There are a lot of code examples today. Code example. One, I think it is called, let me see. So I'm just going to write the name so that when you look at the notes and compare it against the folder, you'll make sense of it. So what I have first is, yes, it's called, the folder is called control partitioning PD. Here what I do is I look at a system like mq double dot plus c q dot plus gq equals f, where I took some random 2x2 matrix, 2x1. This is 2x1, the whole thing. So this is 2x2, q dot is 2x1, g is 2x2, q is 2x1, and f is 2x1. Okay, so these are all random matrices. What I did was, one, I applied f equals minus kp q minus q dot. Effectively, I wanted to be controlled at to 0 speed and 0 position, so minus kp kdq. I also tried f equals m minus kp q minus kdq plus c q dot plus gq. Okay. So both of these are in the code. So let's go to code. So when I'll be sharing this with you, this is the folder which I was talking about, control partitioning PD. If you open that, just as one file. Okay, I have it opened here. So this system is just some random mass matrices. So I just made some 2x2 matrix, some 2x2 matrix for C, some 2x2 matrix for this case, actually also same as G. G is same as K. Okay, I also have like m hat, c hat, k hat. What this does is basically takes m, c, k and just adds some random constants to this, so it's not the perfect model. And so what I did then was I have a controller which is based on Yeah, so I just have a controller based on control partitioning here, not the PD controller which I wrote down notes. I'll cancel that. This basically assumes that you have perfect estimate of the state. So you know what M is, you know what C is, and it's basically pulls the system from the 0 position. So here, let me run this and see what output we get. Okay, so here I'm trying to go to 0.5 and 0.1. You could also have a case where it starts from zero value. Sorry, starts from 0.5 and 0.5 and goes to 0. So here I just decided I'm going to go from 0 and get Q2 to go to 0.1 and Q1 to go from 0 to 0.5. Okay, for that, I have this Q desired, which is 0.5 and 0, and Q dot is basically the velocity. So now, if you look at this, it immediately goes to 0.5 in like less than, I don't know, 0.25 seconds or something like that. If I change this, and instead of this, add the imperfect estimate, so M hat, C hat, and K hat, and run this, it still can do a pretty good job. Takes a little bit more time, and there's probably a little bit error here. You can't see it because of the scale, but a slight error, but it still does a good job even with a bad estimate. Okay, so that's one. Let's we just modify this. There's a different one I was trying to do here, and I got confused. This is not what I showed you. What I showed you was, in fact, this. So to make a modifications to this. Q minus Q desired. This is the first one. And then the second one I showed you was F equals M hat minus KP, Q minus Q desired, minus QD, Q dot, plus C hat, Q dot, plus G hat, Q, where M hat, C hat, G were estimates, and you did not have a good estimate. So this was not in the code. Okay. Okay, now let's look at a real physical system. How about pendulum? So let's look at example. Again, this is all illustrated in code. One link pendulum. Here the goal is we have a pendulum which is horizontal. Let's say this is the mass. Here theta is 0. Our goal is to apply a torque which will get the pendulum in the upright position. So this is theta equals pi divided by 2. So this is the start. This is our goal. And obviously we want to do this as fast as possible. Right? So the system dynamics are MQ, Q double dot, plus CQ, Q dot, plus GQ equals tau. It turns out that if you simplify these equations for a pendulum, you get ml square theta double dot plus, I think there's inertia, I plus ml square. This will be 0 plus mgl sine theta equals tau. And then I try actually two controllers here. Let me move this to the next page. So here I try two controllers. One of them is what you'd intuitively do, which is you just say Kp Q minus Q desired minus Kd Q dot, where Q desired would be you want it to go to 90 degrees. So you'll put pi divided by 2. Okay, so that's like simple PD controller, which you might have seen. You might have done it in a dynamic systems and controls class. The other one is the feedback linearization, which does this. M minus kp q minus q desired minus kd q dot plus c q dot plus g of q. So what are these things? For the system, m is I plus ml square. Q desired is pi divided by 2. That's our goal. Here it turns out that c is 0 because c was 0. And then mg, g is basically mgl sine theta. Okay, so what we'll do is we'll compare the performance of a naive PD controller versus feedback linearization. So the file which, or the folder which has all this is called something like this, 3A pendulum PD. This is the folder. This folder.